recording. There we go. That looks like we're recording. So hi, everybody. I'm Kim McKenzie. With me is Tess Greenock, and we're the Research Data and Scholarly Communications Librarians here at Umass Medical. And we're here to talk about Research Data Management 101, Setting Yourself Up for Success. And we're using that title because these are not just skills that you can use individually during your postdoc or as a grad student, if that's where you are in your career, but also in the future when you're setting up your own lab, if that's the path that you choose to take. So working on these skills now will really make for a smoother road for you in the future. But before we get started, we want to say thank you to the Office of Postdoctoral Scholars, the Center for Biomedical Career Development, and the Graduate School of Biomedical Sciences for giving us so much support and help in getting this seminar series started. The general agenda for today's workshop, we're going to talk for a few minutes about why you would want or need to manage your research data, followed by an overview of storage and backup, file naming and organization, and metadata and readme files. But first, a warning. We're going to be bringing up some data horror stories. So these could lead to fear, anxiety, insomnia, nightmares, and panic attacks. And I can attest to the nightmares because I've had a few data and grad school nightmares this week as I've been creating these slides, and I've been done for 8 years. So it doesn't go away. But we, as your librarians, are here to help and listen to if you have these problems, but also there's always counseling. I wish I had done that. So let's start with some definitions. What is research data management? First of all, data management is a verb, okay? It's something that requires intentional effort and encompasses all aspects of the data lifecycle, from data collection and organizing, all the way through to sharing and archiving your data. What we are not talking about when we say research data management is data science or statistics and analysis, computational science, database administration, a research method, or scientific writing. So that's not what we're going to be going into here. So let's talk about the broad question of why you would want to worry about managing research data. There are 3 very good reasons that we're going to go through. It makes your life as a researcher easier. Funders require it, and it's just the right thing to do. So how does it make your life easier? Managing your data will keep you more organized and efficient. You'll be able to find your files when you need them. You'll avoid data loss because you'll know where you've saved your files and you'll know what version those files are, which we'll talk about again later. You'll satisfy legal obligations, such as data management mandates from funding or from funders. And having clean and easily shareable data sets can lead to increased citations and credit for your work. And having that clean and organized data set will make life easier for others, such as the grad student who might take over a project when you leave the lab you're in, or when either you or someone else tries to build on your data in the future. There we go. The second reason is that funders require data management plans. In 2019, the Open Public Electronic and Necessary Government Data Act set into law guidelines that had been set up in 2013, requiring federally funded data to be published in open, machine-readable formats. And what does federally funded data refer to? Research funded by a couple of agencies you might have heard of, the NIH and the NSF, along with other government agencies. And the NIH has recently set a new policy that will become mandatory in January 2023, requiring the submission of a data management and sharing plan, as well as actual compliance with that submitted plan. And this will be taking effect right about the time when some of you are submitting your first R01s, I would imagine. So if you'd like to read more, we have a link here, and we will be sending these slides out later for you to look at. And finally, you would want to manage your data because it's the right thing to do. Your data are organized and well documented, preserved and accessible. The results are going to be high quality data that's easy to share, which is really, particularly at a time when reproducibility is a big issue. You want your data to be easy to share. And by sharing your data, you can increase citation rates and credibility. Reuse of data can also be a cost saver. Why pay to rerun an experiment that has already been run if that data is already out there? So now we're going to move on to talking about data management plans in particular. But first, Tess, if you could put that poll up. Take a look at this overly complicated looking image. Let's see, can you see the image of the data lifecycle? And, oh, I'm sorry about that. And let me know where you think your data management plan should be written. Or at what point in time, I should say, should you write a data management plan? Okay. For those of you who said, thank you, Tess. For those of you who said proposal planning and writing, excellent work. You'll get your funding for sure. Stop share results. So yes. Okay. Yeah. So yes, you would want to write your data management plan at the point you are creating your proposal or writing up what it is that your research project is going to be. A data management plan is a formal document that outlines what you'll do with your data during and after your research. It should be created, as you said, before you start your research. And as mentioned before, in many cases, you will have to submit this type of a plan when you're applying for funding for your project. Now, the general components of a data management plan include information about the data being collected, what standards for data and metadata are relevant, and we'll talk about that in a little bit, as well as how you plan to share, reuse, or preserve your data. Since you're often submitting this along with requests for funding, budget needs for your data management can also be included in this general data management plan. Now, that sounds like a lot, but there are tools to help you, as well as librarians, such as Tess and I and the other librarians in our group. But DMP Tool is a resource that can help you create a plan with Umass Medical specific guidance. If this is something you want to sign up for now and kind of just play with to see what it's like to set up a data management plan, so you have an idea of what you will be looking at in the future. And there's a link down here. Again, we'll be sending you out these slides. Okay, so I want to warn you that the next part of this talk could be a little bit anxiety inducing. And the next slide might be particularly scary. So let's talk about storage and backup. Data storage, backup, and security are fundamental components of a data management strategy, and a data management plan must account for all three. Well, right now, just a quick show of hands in the participants list. Who can say that they know where and how often their data is being backed up? So far, no one. I don't know if that's because you're not answering or because you don't know. That's okay. Let's move on. So why worry about data storage? So you don't experience what happened to this grad student who not only had his laptop with his thesis stolen, but also the external hard drive that he had stored his backup on. They were in the same place and both were stolen. Unintentional damage happens all the time. Liquid might spill on your laptop, or your cat might push it off of a high table. Stuff just happens, and you need to be aware of that. And unintentional, or sometimes the unthinkable, also happens. In October 2012, Hurricane Sandy hit New York City, and NYU research labs lost years of data in cancer and neuroscience research due to power outages and flooding. And this is not an isolated incident. After quite a few hurricanes and storms due to power outages or flooding, people lose access to their labs, or they lose their data altogether. So it's clear why data storage is important. And as Dr. Varasagi said, is quoted here after Hurricane Sandy, it's not very different from someone losing their entire home. For scientists, their research is their lifeline. And we also need to consider the longevity of data. So this research from 2014 found that for every year increase in an article age, the odds of that data being available for other people fell by 17%. So it's 17% per year decrease in the availability of data. But while this is going to vary by discipline, proper data storage can help to alleviate this problem. And part of data storage that we're going to talk about just briefly is data formats. What format are you storing your data in for the long term? The best chances for long-term access lie in data formats that are non-proprietary, unencrypted, and uncompressed. And what do I mean by non-proprietary or proprietary? That means a format that doesn't rely on a particular program that you generally need to pay for, like Microsoft, in order to open. Not only is it hard to open a Microsoft document, perhaps in another program, if you tried now to open a Microsoft document from 15 or 20 years ago, your Microsoft might not be able to do that. So instead, you want to choose some non-proprietary file formats to store your data in for the long term. So maybe instead of saving that Excel file in Excel, you would store it as a CSV file, which is more likely to be able to be opened 15 or 20 years in the future. Now, where do you want to store that data? There are plenty of options these days, from your computer hard drive to the cloud. And once a data set is complete, repositories, such as eScholarship here at Umass Medical, to store and make your data accessible to others for the long term. They each have their benefits and drawbacks, you know, from your laptop to an external hard drive to a network drive or cloud storage. But what we really want you to remember is what we call the rule of 3. So you want to make sure that you have 3 copies of your data in at least 2 different types of storage device, and 1 should be stored offsite. So one of your copies should be stored perhaps on your laptop, and 1 on an external hard drive, and 1 in the cloud. You just want to make sure that they're not all 3 stored in the exact same place, lest what happens to that grad student who lost their laptop and their external hard drive happens to you. You just never know. So what are your options here at Umass Medical? There are your issued computers, of course, plus the personal cloud storage we have through OneDrive. Many departments have networked drives. In the library, we call it the R drive. Different departments might call it something different. But it's a central location to store copies of all important files that should be saved for the long term. Excuse me, the long term. RedCap is available for data collection. Dropbox is always a good choice. It's a cloud choice where you can store your data. And then for larger data sets, Umass Medical has access to the Mass Green High Performance Computing Center, which is in Holyoke. And it's a repository that we share with a number of other research universities in Massachusetts. So for large data sets, that's also a possibility. So if you've got your data stored in at least 3 places, that's great. But what happens if disaster strikes your laptop and you forgot to resave your last 3 weeks worth of data collection on your external hard drive? So please, if you take nothing else from this presentation, please make sure you have a system for backing up your data and files on a consistent basis, okay? A frequent data backup. I'm not going to go into all of the ways that you can do this, but automation is fabulous. Automate everything you can in your life, but especially your data backups. And while that's great for your local copies, you have to remember your external storage. This needs to be continuously updated as well. One nice thing about OneDrive is that it will just update your data as long as or your storage as long as you set it that way. But that's something that you have to pay attention to and make sure is happening. So you need to create a system for your data backups. You need a personal system, and then someday, if you choose the path of running your own lab, you'll need a lab-wide system. And this should be set up to automatically back up everybody's data, and a plan that can and should be discussed with the members of your lab so that everybody knows what's going on and understands the system. So a quick poll as we switch from my slides to Tess's. How many of you have discussed data management with your PI? Get quite a mixed bag of responses there. Yeah. It's not always discussed, and it's very important to discuss. Tess, over to you. But you're on mute, so you need to unmute.
There you go. All right. Hello. I always wanted to say too, if you do have questions as we're talking, feel free to put them in the chat. And we'll answer them at the end. We do have some time set aside for questions. So, without further ado, I'm going to move on to organizing your data, which is the next step after you've planned how you're going to store your data. And so there's no better place to start when talking about organizing data than file names, since they're the most basic component of organization and the chief identifier of a file. Three elements of a good file name are organization. The organization created by the file name should help you access and retrieve the file in the future. With context, the file name should provide context such as content-specific and descriptive information. And consistency. The file naming convention should be easy to remember and follow to ensure that all files are named consistently to include the same information in the same order. I'm sure we've all seen a folder like this or something similar in our lifetime. You don't have to admit if this folder might resemble something that you've had in your past. I certainly won't be admitting it. But are these names helpful for identifying a file today? What about in 5 years? You think you'll remember, but over time, details fade. So investing time at the beginning in creating an efficient system can save time in the long run. File names are often generated by machines that generate data, such as the first example, 000134Z, or spontaneously named, such as the second example. Maybe the person that came in for the MRI, which is on the right here, was a man with a bow tie, and I cropped the file, so I added the modifier. But using a naming convention can convey more information in a systematic way, as in this example at the bottom of the slide, 2018-0611 underscore P19908 underscore MRI underscore CTG underscore 001.jpg. So why did I choose this file naming structure? The number sequence at the beginning, 2018-0611, is the date the image was taken and follows the date standard set by the International Standards Organization, which is year, month, day. I strongly recommend using this format whenever you're using dates in file names or data collection. Using the standard means that you don't have to question whether the day or the month is the first 2 digits of the number. This is always something that gives me a headache when I'm switching between Canadian and American forms. And when you use a date standard in your file names, you get the added bonus of when you order your files by name, you'll also be ordered chronologically. The second part of the file name is the subject number, then MRI indicates the test. And I included my initials since I'm working as part of a group. I want to identify that I collected the data, so if someone has questions, they would know who to contact. And the last part of the file name is an accession number, so I can give a unique number to each photo. Since I know that I'm planning to have over 100 MRI scans for each patient, I've added leading zeros to my accession number, so I'll be able to see my MRI scans in order when I sort my files by name. Making sure that you have the correct number of leading zeros allows for scale and growth in your file names. Another thing I want to point out about this file name is I used underscores instead of periods or spaces, because like many special characters such as an ampersand or dashes, these are parsed differently on different systems, and they are also often used for specific tasks in a digital environment and can cause problems during data analysis or when sharing data. And a period should only be used in front of a file type extension, JPEG in this case. What you include in your naming structure is up to you, but you should include as much descriptive information that will assist identification independent of where the file is stored, and avoid generic data file names such as data or figure1. Other components you may want to consider including are the research team or group, the project number, or the version number, and I'll get more into this in a minute. There are also different strategies when ordering the components of your file name. The previous example was ordered as date first, but type first and subject first are also good options. You can also force ordering through using numbers at the beginning of your file names. The best strategy is the one that works best for you and your team, and that you will all remember. As I mentioned, I will get back to versioning in a minute, and here it is. It's also important to identify and distinguish the versions of research data files consistently, and this ensures that a clear audit trail exists for tracking the development of data file and identifying earlier versions when needed. Thus, you'll need to establish a method that makes sense to you that will indicate the version of your data files. And some tips for doing this to keep in mind is to use ordinal numbers, 1, 2, 3 for major version changes, and then the decimal for minor changes. Beware of using confusing labels such as revision, final, final 2, final final, definitive copy, etc. And discard or delete obsolete versions. As Kim mentioned earlier, an auto backup facility is, rather than saving or archiving multiple versions, is also very useful. And you can also, by turning on versioning or tracking collaborative documents, or storage utilities such as Wikers or Google Docs will also save you this versioning hassle as well. So in summary, when it comes to file names, remember the 5 C's. Be clear, use terms that anyone can comprehend, avoid jargon or acronym. Be contextual, use terms that describe the content of the file. Be concise, try not to exceed 25 characters. Be consistent, follow the established convention for all relevant files. Be correct, and employ the designated syntax and spell correctly. Now let's put what you learned to the test. What is the best file name? Nice, looks like we all got it. Great. So once you have all your files, have great file names, there are a few different ways that you can organize them. The 2 most common organizational methods are hierarchical and filing, or tag-based and piling. Both of these methods have their pros and cons. Hierarchical items are organized in folders and subfolders. Most operating systems default to this way of organizing files, and it's well adapted to location-based finding. But some of the common issues with hierarchical systems include that it's hard to set up and maintain, it's hard to balance depth and breadth, and items can only go in one place unless there are duplicates, and it's time-consuming to reorganize. The tags-based system, on the other hand, each of the items is assigned 1 or more tags, and it's a very flat system. And because an item can have many tags, it has more flexibility in how a file is categorized. And this can be quicker and easier than hierarchical filing. And one example of this, the tagging tools is tables. And you can also find these tagging features often available in citation management software as well. And it can aid with search-based retrieval as well. But some of the common issues with tagging are that it's not how operating systems store files, and the tags must be applied consistently and correctly, or you get a proliferation of tags. So you'll get tags with just small variations when they really should be 1. It also poorly represents structure of information. You don't have to use either of these systems on their own. You can combine them if that's what works best for you. The same naming best practices that we use for files also apply to folders. So on the screen is an example of a well-organized folder structure with major headings and logical subheadings. This is one place for everything. Regardless of the method you choose, hierarchical, tagging, or a mixture, the most important aspects to both are plan and then follow the plan, and file things immediately according to the plan. Finally, archive what you don't need. Decide on what your final data sets are, and once your project is over, separate obsolete data and decide what you need to keep for the long term, such as data supporting publications or patents, etc. And move files and folders to an archive or old files folder. I like to use the folder called Z archive because I just named my folder archive. It would likely be near the top, so adding the Z at the beginning puts it at the bottom of the list and takes up less valuable real estate in my file viewer. Overall, organization is a means to efficient research, not an end in itself. There's extra work involved when collecting material, but this will pay off in the future when you're trying to find a file and prevent problems. When creating an organization system, it's about finding a balance between having to do too much and doing too little. There's also no one right way to do it. So find what works best for you and your team. And if you need help developing a strategy, we're here to help. Once you've established a system, document it and be realistic. Now for a quick scenario. Say, for example, you're working in a lab and your PI says that they have a whole bunch of pictures of patient kidney biopsy samples on slides, and they would like you to digitize them. The grad student who had started the project has left, and they really need these last few slides digitized for the machine learning test dataset. Good news, the grad student already has the folder set up. So if you just digitize this picture, which of the existing folders would you put it in? And Kim will open that poll. And you may find that it might be hard to decide. So put in the chat, what do you think would have made this question easier for you to answer? Is there something that could have been added to the file or to the biopsy samples or in the folders themselves? So yeah, so maybe if the study ID was on the file, that'd be nice. All right, I'm gonna go ahead and close the poll. So this was a little bit of a trick question because just by having those folder names, we couldn't tell where we should be putting that kidney biopsy sample scan that we just made. So, but what we heard in the chat is that it would have been nice if there was more information included with the file so that we would have a better understanding of where to store it and probably a better way of finding it as well. And this comes along with data documentation, which includes metadata, data dictionaries, and README files. So starting at the top of the list, what is metadata? It is fundamentally the information we create, store, and share to describe things, and it's often called data about data and is synonymous with data documentation. The metadata is usually digital and pervasive in information systems and structured to some degree. In other words, specific elements are collected and stored. When it comes to research data, metadata helps you understand your data in detail and helps other researchers find, use, and properly cite your data. Here's an example of real-life metadata from the Drive repository. The submission record displays the project study level information, such as keywords, scientific names, abstract, and so on, and each data file is accompanied by a README text file, which explains what is in the data file and how the data is collected, etc. But why should we create metadata for research data in the first place? Well, it provides an accurate, reliable record of your work. It includes details you will need when it's time to write up the project, supports reproducibility, and establishes provenance, where your data came from and what has been done to it, which is important for commercial applications and patents. And it helps you get credit because it helps other researchers cite your work properly. It also helps manage people risks because people are fallible, we all forget things, and people leave projects for various reasons, whether it's graduating or going to start a bakery. A good analogy about the importance of metadata is a file without metadata is like a can with no label, impossible to understand without opening it. And perhaps even then. And data documentation may seem trivial. However, researchers can get into big trouble if data isn't documented properly. Here's a famous case in point. In 1999, the Mars Climate Orbiter encountered Mars on a trajectory that brought it too close to the planet, causing it to pass through the upper atmosphere and disintegrate. A NASA review board found that the problem was in the software controlling the orbiter's thrusters. The software calculated the force of the thrusters needed to exert in pounds of force. A separate piece of software took in the data, assuming it was in the metric unit newtons. So the spacecraft burned up because engineers failed to properly document the units of measurement so that they could be converted from English to metric. And this was a $328 million disaster. So I'm sure that we all want to include metadata with our data now, but what should we be including in it? So the four most important elements to cover in metadata are the digital context, the name of the data set, and the date last modified and software used, etc. The investigators and stakeholders, so who collected the data, who to contact for questions, the scientific context, why data were collected, what data and instruments used, as well as the parameters of the data. So what are the units of measurement, the definitions of the codes used, any null values that you're using. And finally, another good principle is to think long-term about your data. The metadata accompanying a data set should be written for a user 20 years in the future. What does that investigator need to know to use the data? Prepare the data and documentation for a user who is unfamiliar with your project, methods, and observations. Luckily, most of the time you do not need to decide what elements need to be included in your metadata from scratch, because there are many community-based metadata schemas and standards which outline what metadata needs to be collected and in what format. If you're depositing your final data set in a repository, they will also likely have their own schema, which can use at the beginning of your project so that you will simply copy and paste the contents when you go to deposit. One example is the Miami or minimum information about a microarray experiment, which is the biomedicine standard for the Gene Expression Omnibus repository, or GEO. There are also a number of data standards for clinical research that are managed by the CDISC consortium. If you're not sure if your area of research has a standard already, you can search on fairsharing.org. Across most metadata standards, there are general fields that are common, such as title, creator or author, description, etc. These fields are used not just for data, but for all sorts of digital resources. If you're using a locally developed standard, these are some fields that you want to consider including. If you're developing your own standard, the most important part is to document it and use it consistently. Just as there are a number of standards available to help determine the metadata fields that should be included, there's software and a number of other digital tools that can be employed to create and manage metadata content. There are specialized tools such as the DataCite Metadata Generator, which is a single HTML form which can be used to generate DataCite metadata in XML form. And some of the specialized software is being developed right here at Umass Medical School, such as Omega and the Micrometa app from Dr. Strambio de Castilla's lab. You might also find the right tool for you on this index of metadata tools from the Digital Creation Center in the UK. And automatic metadata is also generated from a number of tools, such as microscopes, cameras, and other instruments you might find around your lab. Where no formal metadata standard exists, or you're looking for a low-tech tool for recording metadata, writing readme-style metadata in a text file is an appropriate strategy, at the very least for internal use. This slide shows the beginning of a readme-style metadata file. You can find a similar template and examples of on the resource guide linked from this page. The template opens up a text file that you can download to your computer and fill in. There's a lot of information you can include in your readme file. The information listed on this slide from Cornell's guidelines are the minimum recommended content that you would want to include if you intend to share this data. As with all metadata, Using the scientific conventions of your discipline for names and keywords will help with making your data findable and reusable. A data dictionary is another metadata collection tool, which represents the structure of your data set. Each row in a data dictionary, which is generally a spreadsheet, corresponds to a field in your data entry form and provides a detailed description of each variable, such as the variable name, meaning, units, format, permissible values or ranges of values, known issues with the data, such as systematic errors, missing values, etc., relationship to other variables, as well as any null value indicators. You would also want to include anything else someone needs to know to better understand your data. In other words, the types of things you want to know when faced with an unknown data set. Not only is such information incredibly useful if you're sharing a data set, but it's also useful if you plan to reuse a data set in the future, or you are working with a very large data set. Basically, if there's a chance you won't remember the details or never knew them in the first place, a data dictionary is needed. Some research data collection tools, such as REDCap, generate a data dictionary for you based on your data collection forms, so that you can reconstruct your database fields if you need to. Note that a data dictionary does not actually include the data you collected. So far, we've been talking about metadata at the data level, but project or study level metadata is equally important to provide the context of data collection, structure and organization of data files, data sources used, information on confidentiality, access and use conditions, etc. This information might be captured in a procedures manual, protocols, or a lab notebook, or code book, or simply a readme file. So you know how I mentioned earlier that metadata is often generated based on what we want to know about a data set itself? So here's an example. What questions would you have about this data, and what would you want to see in the metadata if you were presented with this data here? You can type your answer in the chat. Does everybody understand what the column names are? Column headers? Yeah, what kind of data is it? Why are some of the columns blank? Excellent. What do the blanks mean? Yeah, and which study was this from? Then this is an actual data set that we have in our repository in eScholarship. So there is more information on it. But as you can see, we do have many questions. What's the difference between D gene name and V gene name? What does the letters indicate? So there's many questions, and those are the type of things that you want to think about as someone, when you're writing your metadata, maybe pass it off to a colleague and say, oh, what questions do you have about this data? Might be help you with thinking about what metadata you need to include. So in the past 40-ish minutes, we've thrown a lot of information at you, but we hope you'll be able to take away at least one tool or strategy that you can use in your own research, whether it's the knowledge that research data management makes life easier for yourself and others, the rule of 3, store 3 copies of your data in 2 different media and at least 1 offsite, that great file names are clear, contextual, concise, consistent, and correct, that data documentation should be written for someone 20 years in the future, and to use available data and metadata standards. If you're looking for more information on research data management, I recommend you check out our resource guide. There's also some great resources on there to learn more, such as classes and webinars. And speaking of webinars, our next seminar is going to be presented by our library colleague, Sally Gore, on the library services available for researchers. So if you're new to UMass Medical School or know someone who is, or are curious about the services the library has to offer, keep an eye out for registration and information coming soon. And in the new year, Kim and I will be back with our January seminar, Making Research Metrics Work for You. So I want to take a quick moment to thank you so much for learning with us today. We are constantly learning and growing as instructors, and really appreciate if you could fill out this 2-question assessment. And I will put the link in the chat. Nope. There we go. The first question is one thing you enjoyed or learned during the session. And the second question is one thing in the session that you could be improved or a question you still have. So please do not hesitate to reach out to us if you have with any research data management questions you might have in the future. We'll be sending the slides out, as Kim said, to all attendees after the presentation and the link to the recording. And if there are any questions, we are happy to answer them now. I think I saw one in the chat.
There was one in the chat.
All right.
Your laptop has 10 gigs available. I would say this is a great point to talk with your PI about getting perhaps an external hard drive to store some data with, but also whether there's a departmental networked drive that you can also use to store data in, because there are multiple different ways that you could find more storage space for your data. And if anyone has any other questions, you can go ahead and ask. Okay. Thank you very much.